Hey everyone, my name is Jimmy. I'm a former LinkedIn software engineer who spent the last 3 years helping others prepare for the coding interview. In this video, we're going to break down the post-order traversal, which is really the most important technique we need to know when we're solving binary tree questions using recursion. So we're going to start by looking at a classic interview question that's going to teach us the motivation for the technique. Then we're going to look at how it can be applied to 3 additional questions, including a hard question that is frequently asked by all of the top tech companies. So if you like this material, please don't forget to like, comment, and subscribe. And don't forget to check out the link in the description below for a free interactive visual guide to all of the most important coding interview patterns. So the first question we're going to look at is diameter of a binary tree. We're first going to look at the brute force approach to the problem. That's going to help us understand why the post-order traversal approach is necessary. This is a pretty well-known interview question, so if you are already familiar with it, feel free to skip ahead to the 10-minute 30 mark where we talk about how the post-order approach can be used to solve problems in general. In this question, we are being asked to find the diameter of a binary tree, where the diameter is defined as the longest path between any 2 nodes in the tree. If we have this tree on the left, then the diameter is going to be this path right here between nodes 5 and 3. And specifically, we want the number of edges on this path, which is going to be 1, 2, 3, 4, 5 in this case. The diameter of a tree does not have to go through the root. For example, in this tree right here, the diameter is this path, and it has a total of 1, 2, 3, 4, 5, 6, 7 edges. So let's say we have this binary tree right here. The diameter is this path between nodes 4 and 3 for a length of 1, 2, 3, 4, 5. The first thing we want to note is that the diameter of a binary tree is always going to exist between 2 leaf nodes in the binary tree. So our algorithm is going to look like this. We're going to visit every single node in our binary tree, and at each node, we're going to calculate the length of the longest leaf-to-leaf path that runs through that node. And after we finish visiting each node, we can return the longest of those paths that we've found. So there are 2 ways to execute this algorithm. The first is from the top down. What this means is we're going to start by finding the longest path that runs through the root node. Now, how do we do this? Well, the longest path that runs through the root is just going to be equal to the height of the root node's left subtree. So this has 1, 2, 3, 4 for a height of 4, plus the height of the node's right subtree, which is 1. So once we have those 2 values, we can add them 2 together to get the length of the longest path that runs through there, which is going to be 5. So after we finish getting the length of the longest path running through the root node, we're going to move on to the next node in the tree and do the same calculation here. We're just going to follow that same process, find the height of the left subtree. This is going to be 1. Then we're going to find the height of the right subtree, which is 3 in this case. We can add those 2 numbers to get 4. So we're going to do that same process for every single node in the binary tree. And you might be able to tell that there's a lot of repeat work being done. In particular, at each node, we have to traverse all the nodes below it to find the height of the left and right subtrees. Now, all that repeat work leads to a big O of n squared runtime, which is not going to be good enough for the coding interview. So here's the code for this top-down approach. We have this function diameter right here, which takes in a node. And the first thing this function does is it gets the height of nodes left and right subtrees using this recursive function here. After those values are returned, it then calculates the longest path through the root of this subtree by adding left height and right height together. And after that, it moves on to finding the longest path that runs through the node's left subtree. And so this is where that repeat work is coming from. Every time we recurse one node further down to get its longest path, we have to find the height of that node's left and right subtrees. So you can kind of think of this as a nested for loop of sorts. And again, this has the big O of n squared runtime. So now let's look at the bottom-up approach to this problem. Instead of starting at our root node, we're instead going to want to think about starting at the bottommost node in our tree, which is this node right here. And when we're at this node, we want to do the same thing we did before. We want to calculate the length of the longest path that runs through this node using the heights of its left and right subtrees. So this node has empty left and right subtrees, so they're both going to have height 0. And now node 3 can take those 2 values, add them together to get the length of the longest path, which is 0. So let's just write that value down here in a variable called max. We'll talk about this variable a little bit more when we look at the implementation of this bottom-up approach in a second. But for now, let's keep on going on with the process. So after node 3 is done finding its longest path, it's going to return its height to its parent node, and that height is 1. And after it returns that height, we're done with it. We don't ever need to visit this node again. And now node 1 has part of what it needs to calculate its own longest path. It also needs the height of its right subtree. So eventually this node will pass in its height right here. This is going to be 1. We're done with this node. Now node 1 has the height of both its left and right subtrees. So it's going to add them two together and to get 2, which is just this path right here. Okay, so now the max path that we found so far is 2. So we're going to update that. And this is just saying thus far, after all of the nodes that we visited, which are the nodes in this subtree, we have found a maximum path of length 2. So now node 1 is done calculating its longest path. It's going to return its height back up to its parent, which is going to be 2. We're done with these entire nodes. This is going to return a 1. So now we're going to add these two together, 2 plus 1, which is 3. Update our max. Now we're going to return our height to our parent. So this is going to return a 3. We're done with these nodes. This returns a 1. Okay. And then we're going to take these two numbers, add them together, which is 4. And since we're at our root, we visited every single node and we can return that our diameter is 4. So this bottom-up approach is the optimal solution to this question. Because we visit each node in our binary tree once, the runtime for this algorithm is going to be big O of n, where n is the number of nodes in our binary tree. So here's the code for our optimal solution. We'll see that we have a single recursive function that returns the height of the subtree rooted at a given node. It also calculates the length of the longest path that runs through that node using the values of the heights of its left and right subtrees. You can see that's being done right here. And you notice that this calculation of left plus right is done after the recursive calls. And that fact right there, the fact that it's being done after the recursive calls, is also known as a post-order traversal. And it's what gives our algorithm bottom-up behavior that we just saw. So we're also using this global variable max right here to store the length of the longest path in our binary tree. The reason why we want to use this global variable is because our recursive function returns the height of each subtree, and that's different than the value that our question is asking for. And so by using a global variable to store the longest path that we've seen so far, we're able to keep this return statement simple. And in my opinion, that just makes it easier to tell what the recursive function is doing. And you can see that we don't return the result of the recursive function at the end. We just return the value stored in max after the recursive function has finished executing. So now let's visualize a few steps of this algorithm so we can just get a complete understanding of how everything works. So the first step is to initialize that global variable max. Now we're going to start our recursive function at the root of this binary tree. Now this recursive function is trying to calculate both the longest path that runs through the root node and the height of its subtree. To do that, it needs to know the height of its left subtree. So we're going to recurse left subtree, recurse. Okay, so now we've reached our first base case where node is none. So we're going to return 0 to its parent. So now node 1 has the height of its left subtree. It's going to get the height of its right subtree, which is 0. So now at this point, node 1 has received the height of both its left and right subtrees. So now it can calculate the length of the longest path that runs through it using those two values. So it's going to do left plus right, which is still 0. So max is still 0. We haven't found a longer path than 0 yet during our traversal. And now we're going to return the height of our subtree back up to our parent. Okay, so now at this point, our parent has the height of its left subtree. It's going to move on to finding the height of its right subtree, which is going to go through a few base cases like we just saw. Okay, right here, this is a base case. So now, like before, node 4 has the height of its left and right subtrees, adds them together. Now it's going to return 1 to its parent. So now node 9 has the height of its left and right subtrees. It's going to add them two together to get 2, and then it's going to update the variable max right here. So max is updated. This just means we found a path of length 2 so far in this subtree, which is all of the nodes that we visited so far. And now we're going to return our height to our parent, which is max left plus right plus 1, which is 2. Okay, so this just continues until we visited every single node in the binary tree. Let's just go over the complexities one more time. The time complexity of this algorithm is going to be big O of n because we only visit every single node once. And the space complexity is going to be O of h. And this is just due to the nature of depth first search, which means we'll have as many of these call frames on the call stack as there are nodes in the height of our binary tree. Now let's summarize what we just covered. There are two approaches to the binary tree problem. The first is the top-down approach, which has big O of n squared runtime, which is not good enough for the coding interview. The other approach is from the bottom up. Here we think about first calculating the longest path that runs through the leaf nodes of the tree. The leaf nodes then return their heights up to the parent, which then use those values to calculate its longest path. And we work our way up the tree, only visiting each node once, and that results in the optimal big O of n runtime. Now, this bottom-up approach is also known as a post-order traversal, and that's going to be the focus of this video from here on out. So, when do we need to use this post-order traversal? So, whenever we need to calculate something at each node in a binary tree using values from that node's left and right subtree, we're going to need to use this post-order traversal in order for us to get the optimal solution. So, in our diameter example, at each node, we needed the heights of the left and right subtree in order to calculate the length of the longest path that runs through each node. And if you notice in the code, we're calculating the length of the longest path through each node after the recursive calls to its left and right subtrees have finished. And that's what gives the post-order traversal its name. We're processing the current node after its left and right subtrees. Let's now look at another example of a question that uses this post-order traversal. So in this question, we're being asked to find the tilt of a binary tree. This question is rated as an easy only code, so it might be something you see in the earlier rounds of your interview, like during a phone screen, for example. But regardless, it's a great question for us to start applying the concepts we just learned about the post-order traversal. So here we're given a binary tree and we're asked to find its tilt. Now the tilt is something that can be calculated at each node, and it's defined as the difference between each node's left subtree and right subtree sum. So in this case, the tilt here at this node is going to be 9 minus 2. We want to take the absolute value of that. So at this node, it's going to be 7. And these have empty left and right subtrees, so these are going to be 0 and 0, okay? And the tilt applies to every node in the binary tree. So in this case, this is 1, this is 4. So the tilt at this node is going to be 3. The tilt at this node is going to be 7 minus 3, which is 4. And then in order to calculate the tilt at the root node, we have to sum everything up here. So this is going to be 14. This is going to be 12. Okay, so 14 minus 12 is 2. So we want to sum up all of these numbers together. So 3 plus 4 plus 2. So the tilt of this entire binary tree is going to be 9. First thing, what makes this a good question for using that post-order or bottom-up approach? It's because at each node, we need to calculate something based on the values of our left and right subtrees. In particular, we need to know the sum of our left and right subtrees in order to calculate the tilt at that node. And now when we actually work through how to solve this problem, remember to work from the bottom up. So we're going to calculate the tilt at this node first. Well, its left and right subtrees have sums of 0. So 0 minus 0 is 0. So at this node, the tilt is 0, and we can store that in this variable here. Now when that's done, what do we need to return to its parent, to our parent, so it can calculate its tilt? Well, we need to return the sum of this entire subtree. So this is going to return a 1. Same thing. Okay, now we're going to move to 4, 0, 0 here. Tilt hasn't changed. This needs to return the sum of its subtree to its parent, which is going to be 4. Now when node 9 has those two values, it's going to subtract them in order to find the tilt at node 9. Okay, so 4 minus 1 is 3. We're going to update this value right here. Now what do we need to return to its parent? We need to return the sum of this entire subtree. So that's going to be 1 plus 4 plus 9, which is 14. And that's going to continue in depth first search fashion until we've visited every single node and we can have the tilt for the entire tree. And again, this bottom-up approach is going to let us do this in big O of n time because we only have to visit each node in our binary tree once. So I'm going to leave the implementation up to you. I left a link to this question on hellointerview.com where you can practice it. It's going to look a lot like the solution to diameter of a binary tree, but work it out for yourself because it's just a really good question to get more comfortable with this post-order traversal. So now on to question number 2. So in this question, we are being asked to find the longest Univalue path in a binary tree. And that is just a path where all of the nodes along that path have the same value. So in this case, this is one Univalue path between nodes 2 and 2. But this is going to be the longest Univalue path right here because all nodes along this path have the same value 3. And what we really want is the number of edges along that path. So this is going to return 3 in this case. And just like the diameter of a binary tree question, this longest path does not have to pass through the root of our binary tree. So our approach to this problem is going to be very similar to the one that we used to find the diameter of a binary tree. So let's quickly revisit that solution so we can understand what each value that each node gets from its left and right subtrees and how that contributes to finding the longest path. So in the diameter question, each node returned the height of its subtree to its parent. So this node is going to return a 2 to its parent, while this node returns a 1. And let's really understand what this value 2 represents here. So from node 3's perspective, this value 2 represents the longest path from its left subtree that node 3 can extend as part of the longest path that runs through node 3. And how does it extend that path? It extends it by combining the longest path from the right subtree, okay? So if this 2 just indicates this path right here. And when we calculate the longest path that's going through node 3, we want to extend that by combining it with this path. And that gives us the longest path that's running through node 3. So we can visualize it as basically gluing the longest paths from the left and right subtrees together in order to get the longest path that goes through nodes. So understanding each return value as the longest path that can be extended by its parent is really the key to solving these longest path binary tree problems. So now let's look at how we can apply that same principle to this question of finding the longest Univalue path. So our algorithm is going to work by visiting each node in our binary tree, and at each node we're going to calculate the longest Univalue path that runs through that node. There are no Univalue paths that run through any of the leaf nodes, so at this node it's going to be this path, and this node it's going to be this path, and at the root it's actually this path right here. And we want to take the longest of those paths for this path 1, 2, 3. So let's visually understand how we're going to find each of those paths using the bottom-up traversal. And we're going to really focus on the return values that each subtree returns to its parent, which represents the longest path that can possibly be extended by its parent, okay? So let's look at our node here because we're going to start at the bottom of the tree. The longest path that can be extended by its parent actually has a length of 0, and we'll find out exactly why in a second. Same with this node, this is going to return a 0. So now we're at node 2. We want to calculate the longest Univalue path that runs through it using these two return values right here. So the first thing we have to check is if our node is equal to our left child. Because when that's true, we're basically allowed to include this edge right here as part of the longest Univalue path, and we're able to extend it using whatever value we got from our left child. So in this case, that's a 0. So same logic applies to our right child. They have the same value. We can think about extending this edge right here. So for a 1, and so now the longest Univalue path that goes through this node is going to be 1 plus 0 plus 1 plus 0, which is going to be 2. So we're just going to store that value in this variable max right here. So now we're done with node 2, and we want to return a value up to our parent. And we want to return the longest Univalue path that can possibly be extended by our parent, okay? We can't return this 2 here because our parent can't do anything with this path. It can only exist from one side, okay? So the longest Univalue path that exists on one side is actually either of these. It could be this one or this one. Okay, so it has a length of 1. So node 3 is a leaf node, so it's also going to return a 0. So now node 3 has received both of these values from its left and right subtrees, and it needs to use them to calculate the length of the longest Univalue path that goes through it, okay? So first thing we have to check, 3 is not equal to 2, so we actually can't use this value 1 at all. It's not relevant because we can't include this edge as part of extending our longest Univalue path. In this case, 3 is equal to 3. So we can draw a 1 here. Now we're going to add that to our return value. The fact that they're equal lets us use this return value. So we're going to have a 1 plus 0. That just means the longest Univalue path that goes through this node has length 1. It's not greater than our max, so we don't have to do anything. Now we have to return a value up to our parent. We need to return the longest Univalue path that can be extended to our parent, okay? And that's really just this path right here. So we're going to return a 1. Now, this is a leaf node. This is going to return a 0. Okay, so our root node has to do the same thing, has to use these two values to calculate the longest Univalue path that runs through it, which is really just this path. Okay, so first thing we have to check, 3 and 3 are equal to each other. So we can think about drawing a 1 here. This allows us to use our return value. Same thing here, 3 and 3 are equal. We can draw a 1 here. This allows us to use our return value. So we're going to have 1 plus 1 plus 1 plus 0. Now our max Univalue path that we found so far has length 3. And now if we were to return a value to our parent, let's say there are more nodes up here. If we were, then we would return 2 to indicate this path right here, because again, it can only be from one side. So this would return a 2. But since we are actually done visiting each node in our binary tree, we can just return the value of max. Okay, so this is the approach to longest Univalue path. Just really think about each node returning the length of the longest Univalue path up to its parent that its parent can possibly extend. And the logic for this question is definitely tricky, definitely requires you to think about it in terms of how to implement it. So I'm going to leave that to you. There's a link to the description in hellointerview.com as well, where you can try it out. So the last question we're going to look at is binary tree maximum path sum. And this question is rated as a hard on LeetCode, and it's asked by all of the top tech companies such as Meta, Google, Amazon, Apple, etc. Okay, and even though it's rated as hard, it becomes a lot more manageable once we break it down in terms of what we already know about the bottom up or post order traversal and the way we learn to think about these longest path in a binary tree problem. So this question is asking for the path in the binary tree with the maximum sum. So in this case, it's going to be this path right here between these two nodes for a sum of 3 plus 2 plus 1 plus 3 for a total of 9. And one thing to note is that this path can pass through any node in the binary tree, but it must contain at least one node. So we want to solve this in a very similar fashion to both the diameter and the longest Univalue path questions that we already saw. We want to solve this from the bottom up, and we want each node to return the maximum value path that can be extended by its parent, okay? So we're going to start at this node in the binary tree. And since we know that our path has to contain at least one node, then we can write this down, the value of this node, as the maximum path that we've seen so far. And now what we want to do is we want to return the value of the maximum path that can be extended by its parent. So this is going to return a 3. This node is going to return a 2. Now when we're at node 2, we're first going to calculate the longest path that goes through node 2. So that's going to be 3 plus 2 plus 2 for a total of 7. So 7 is the longest path that we've seen so far. And now we want to return the maximum value path that can be extended by our parent. Okay, so that's actually going to be this path right here. So that value is going to be the largest between 3 plus 2 and 2 plus 2. So that's going to be 5. Okay, and if we just visualize this, this allows node 1, the root node, to use this path as part of its maximum path sum that goes through it. Okay, so now this one's going to return a 3. Now node 1 has enough information to calculate the maximum path that runs through it, which is 5 plus 3 plus 1, okay, which is going to be 9. And if we did have another value to return up, we would return 3 plus 5 plus 1 as the maximum path that could be extended to its parent, but we don't here. So we can just return this 9 at the very end. So this is the gist of our approach. The only other thing we need to talk about is how to handle negative values. To figure that out, I recommend playing around with a few small binary trees with negative values, such as this one or this one. Just really think about what value each subtree needs to send to its parent so that its parent is able to accurately calculate its maximum path that runs through that node. And again, I'm going to leave that up to you. It's a great way to practice your problem solving skills and get practice implementing this question using the bottom up and post order approach that we just talked about. It's going to be it for this video, and I know we've covered a lot, so let's quickly summarize all of the important takeaways. First one is that we want to use this post order traversal whenever we have a question that requires us to calculate something at each node based on values that we need from our left and right subtrees. And in the code for post-order traversal solutions, we're going to first make those recursive calls. Then after getting those values, we're going to use those values to calculate something for our current node. Then finally, after that, we're going to return some value to our parent. And this just allows us to work from the bottom of the tree upwards and solve everything in one traversal, which results in the optimal big O of n time complexity. And longest path questions are a specific type of question that can be solved using the post-order traversal. For these types of questions, you want to think about having each subtree return the longest path that can be extended by its parent. The parent's going to have to work out some logic to see how it uses those values to calculate the length of the longest path that runs through its node and then returns the longest path that can be extended to its parent. Okay, so definitely work through the practice problems that we talked about here in order to really solidify your understanding of how to use that approach. And I've also left a couple of more questions that use this post-order traversal in the description. We just didn't have time to cover it in today's video. Okay, so that's going to be it. I hope this helps you all. Good luck in your interviews. Don't forget to like, comment, and subscribe. And don't forget to head over to hellointerview.com if you want more of these types of breakdowns to the most important coding interview patterns. All right, bye everyone.